In example 32.1, we're going to consider the electric and magnetic fields of a laser beam. In this problem, a carbon dioxide laser emits a sinusoidal electromagnetic wave that travels in the negative x direction. The wavelength is 10.6 micrometers, and the E field is parallel to the z-axis, with Emax equal to 1.5 megavolts per meter. Given this information, we're going to write down the vector equations for the electric and magnetic fields that compose this traveling electromagnetic wave. Well, let's begin with the diagram of the wave. As shown here, it's the x-axis. The wave is moving in the negative x direction with the electric field parallel to the z-axis. When the electric field is positive along the z-axis, we need E cross B to be in the direction of propagation. And by the right-hand rule, I determined that B must be in the positive y direction when E is in the positive z direction. So we can immediately write down equations for the electric and magnetic field as shown here. E is in the k hat direction. It's some E max times the cosine kx plus omega t. And B is going to be in the j hat direction with B max cosine kx plus omega t. There's no relative minus sign here by the argument I just made from the diagram. And the positive sign indicates that the direction of propagation is in the minus x direction. Now we need to determine B max, K, and omega in this problem. So B max is E max over C, and that's going to be 5 times 10 to the minus 3 Tesla. K is 2 pi over the wavelength, and we're given the wavelength, and that's 5.93 times 10 to the 5 radians per meter. And omega is C times K, which is 1.78 times 10 to the 14 radians per second. So here's my final expression for the electric field as a function of time, and here's the expression for the magnetic field as a function of time. I could have also included a phase in these equations, so I could have put plus phi in both of them. But this is not really necessary in the context of this problem. There's no way for me to determine what phi is, so I'm simply going to take it to be 0 in this case. And this ends example 32.1. In example 32.2, we're going to examine the propagation of electromagnetic waves in different materials. In part A, we're going to consider light from a sodium vapor lamp, which has a frequency of 5 times 10 to the 14 hertz. We're going to find the wavelength of this light in vacuum, and then the wave speed in the wavelength in diamond, which has a dielectric constant of 5.84 and a relative permeability of 1. In the second part of the problem, we're going to consider a 900 megahertz radio wave, which passes from vacuum into an insulating ferrite. Ferrite is a common ferromagnetic material used in the electronics industry. We're going to find the wavelength in vacuum again and the wave speed and wavelength of this radio wave in the ferrite, for which K is equal to 10 and the relative permeability is equal to 1,000. So the equations we'll need are first the relationship between the speed of a wave and its wavelength and its frequency. This corresponds to vacuum, and this will correspond to the propagation of light in some material. That speed can be written in this form, which is equation 32.21, which basically is the speed of light divided by the square root of the product of the dielectric constant and the relative permeability. So in part A, the wavelength in vacuum would just be the speed of light divided by the frequency, which again is 5 times 10 to the 14 hertz, and we get 589 nanometers. The speed of the light in diamond is equal to C over the square root of K times Km, and putting in the two values, we get 1.24 times 10 to the 8 meters per second. The wavelength in the diamond, of course, is the speed in diamond divided by the same frequency I used in part A, and I get 244 nanometers. Now turning to the radio wave, the wavelength in vacuum is much longer, is 3.33 meters. The speed of light in the ferrite is, or the speed of the radio wave rather, in ferrite is 3 times 10 to the 8 divided by the square root of 10 times 1,000, and that gives us 3 times 10 to the 6 meters per second. And the wavelength again is the speed of the wave divided by the frequency, which is 90 megahertz, and I get 3.33 centimeters. Notice that these speeds can actually be quite a bit lower than the speed of light in vacuum. So this is about 1/3 the speed of light in vacuum, and this one is really slow. It's about 1% of the speed of light in vacuum. Also note that the dielectric does not change the frequency of the electromagnetic wave. F is the same throughout these calculations. What it changes is the wavelength and the speed. This ends example 32.2. In example 32.3, we're going to examine the energy associated with a non-sinusoidal wavefront. For such a wavefront, the electric and magnetic fields behind the front are uniform, but ahead of the front they're equal to 0. In this case, the electric field behind the front is 100 volts per meter. We want to find the corresponding magnetic field, the energy density, and the rate of energy flow per unit area associated with this wave. So the equations we'll need for the problem are equation 32.4, which relates the magnitude of the electric field to the magnitude of the magnetic field of a traveling electromagnetic wave. Equation 32.25, which gives us the energy density in terms of the magnitude of the electric field of the wave. And equation 32.27, which gives us the magnitude of what's called the Poynting vector, which is the energy flow per unit area. So in part A of this problem, we're going to calculate the magnitude of the magnetic field, which is trivial, is 3.33 times 10 to the minus 7 Tesla. The associated energy density is epsilon naught times E squared, and we have E, and so we get 8.85 times 10 to the minus 8 joules per cubic meter. The Poynting vector magnitude is E times B over mu naught. We just calculated B. Mu naught, of course, is 4 pi times 10 to the minus 7 Tesla meter per amp, and we get 26.5 watts per meter squared. For this last calculation, I could have used equation 32.26, which gives the magnitude of the Poynting vector entirely in terms of the electric field. So that would have been epsilon naught times C times E squared, and I would have gotten the same value. This ends example 32.3. In example 32.4, we're going to consider the energy of a sinusoidal electromagnetic wave. In particular, we're going to consider a radio station on the surface of the Earth that emits a total average power of 50 kilowatts. The signal from the transmitter is detected by a satellite which is 100 kilometers from the transmitter in orbit. We want to calculate the electric and magnetic field amplitudes as detected by the satellite. So the first thing we're going to do is assume that the transmitter emits its energy uniformly in all directions above the surface of the Earth. So this energy makes its way to the inner surface of this hemisphere, which has a radius of the distance from the transmitter to the satellite uniformly. So the idea is first to calculate the intensity independently, and once we have this intensity of the radiation at a distance of 100 kilometers from the transmitter, we can calculate Emax and Bmax from equation 32.29, which is shown here. Notice that the intensity is the average of the Poynting vector, and it can be written in a number of different ways. And of course, we'll use the relationship between the electric field and the field for a traveling electromagnetic wave. The surface area of the hemisphere is 2 pi r squared, where r is the distance again between the transmitter and the satellite. That gives us 6.28 times 10 to the 10 meters squared. The intensity is the power being transmitted divided by this area. So this is the intensity at this distance. And we get 7.96 times 10 to the minus 7 watts per meter squared. This, of course, has to be equal to Emax squared over 2 mu naught C from this equation. And our target variable is Emax, so I can now rearrange this equation and solve for it, where I'm replacing SAV by the intensity I just calculated, and I get 2.45 times 10 to the minus 2 volts per meter. Bmax is Emax over C, and I get 8.17 times 10 to the minus 11 Tesla. It's sort of interesting. This electric field is quite measurable. It's small, but it's not infinitesimally small. The magnetic field associated with the transmitted wave is very, very tiny. It cannot really be detected. So the electronics of the satellite is really detecting the electric field of the traveling electromagnetic wave. And this ends example 32.4. In example 32.5, we're going to look at the power and pressure associated with electromagnetic radiation from the sun. In particular, we're going to consider a satellite such as shown in this figure, which has energy collecting panels of total area of 4 square meters. We'll assume that the sun's radiation is perpendicular to these panels and that it's completely absorbed. Given this, we want to find the average solar power absorbed by the panels and the average radiation pressure force on the panels. So we're going to use the fact that intensity is power divided by area and that the radiation pressure of the sun is 4.7 times 10 to the minus 6 pascals at the distance the Earth is from the sun. So the first part of the problem, we simply rearrange this equation and we're going to calculate the total power delivered to the 4 square meters of panel. And so we multiply I times A, where again at our distance from the sun, the intensity of the sunlight is 1.4 times 10 to the 3 watts per square meter. And we get 5.6 kilowatts. The force on the panels is the radiation pressure times the area of the panels, and we get 1.9 times 10 to the minus 5 newtons. The power delivered to the panels is substantial. It's about 5 kilowatts, which is enough to run a satellite, but the force is very small. It's really negligible. It's interesting, though, if the light were reflected from the panels and not absorbed, then this force would be twice as big. And this ends example 32.5. In example 32.6, we're going to calculate the intensity of the standing wave represented by equations 32.34 and 32.35. These equations specify the electric and magnetic field of the standing wave, and notice that these two fields are perpendicular to each other, but they're not of the form of a traveling wave. In other words, the functional form is sine kx times sine omega t, but for a traveling wave this would have been sine of kx minus omega t, for instance. So the idea is to calculate the Poynting vector, which gives us the intensity as a function of time. The Poynting vector is given as E cross B divided by mu naught, and then we can average this vector to find the intensity. So all we simply need to do is put these two expressions into the cross product, where we note that the electric field is in the j-hat direction, the magnetic field in the k-hat direction, and the Poynting vector is going to be in the i-hat direction, and here's our expression. Recall that the sine of 2a is equal to 2 times sine a cosine a, so I can rewrite this equation in the following way as sine 2kx times sine 2 omega t, and now I need to average it. But the average value of a sine function over any whole number of cycles is equal to 0, so the time average of this is going to be 0. So I find that the net intensity of the standing wave is equal to 0. But this actually makes sense, because the standing wave is comprised of two waves of equal frequency and wavelength that are traveling in opposite directions. So the intensity of one is completely canceled by the intensity of the other. And this ends example 32.6. In example 32.7, we're going to consider standing waves in a microwave cavity. Electromagnetic standing waves are set up in a cavity with two parallel highly conducting walls that are 1.5 centimeters apart. The traveling electromagnetic waves reflect off these walls, and incoming and outgoing waves interfere with each other to produce a standing wave. In Part A, we're going to calculate the longest wavelength and lowest frequency of these standing waves. In Part B, we're going to find where the electric and magnetic fields have their maximum and minimum values, respectively. So the condition for the standing wave is that it has an integer number of half wavelengths contained within the cavity. This means that there's only discrete wavelengths that are allowed, and that's given by this equation, 32.38. And of course, the corresponding frequencies are just the speed of light divided by these wavelengths, and so I have discrete frequencies. The position of the nodal planes of the electric field are given by this equation, and the nodal planes of the magnetic field are given by this equation. Notice that the nodal planes of the magnetic field lie in between the nodal planes of the electric field. So in Part A, we're simply going to take n equal 1, and we find that the wavelength is twice the length of the cavity, which is going to be 3 centimeters. The corresponding frequency is 10 gigahertz. For Part B, with n equal 1, the distance between the cavity walls is simply a half a wavelength, and the electric field must be 0 at these conducting walls. The electric field inside of a conductor is equal to 0. So the nodes have to be at each end of the cavity, and the maximum electric field, of course, must be at the center of the cavity. In contrast, the magnetic field is just the opposite. It has antinodal planes at each wall and is 0 at the center of the cavity. Another way to think of these standing waves is in fact resonant modes of the cavity. So these look like the resonant modes on a string. So this n equal 1 is the fundamental, n equal 2 is the first harmonic, and so forth. And this ends example 32.7.